In this video, I will be talking about two different sorting algorithms, bubble sort and insertion sort, and this will give you a broad idea about sorting in general. So, the sorting problem um, consists of putting the elements of a list in increasing or decreasing order. So, to put them in a certain order. So could be numerical order, could be an alphabetic order, and so on and so forth. Sorting is an important problem because a non-trivial percentage of all computing resources are devoted to sorting different kinds of lists, especially applications involving large databases of information that need to be presented in a particular order, by customer, by part number, and so on and so forth. Again, in the introduction of the previous video, I drew your attention to the fact that your Facebook news are sorted by date. The same happens for WhatsApp messages. So you are usually interested by the most recent, most relevant messages first, and so on and so forth. So it's one of the most famous problems, and it happens that to solve plenty of problems, you often need to call a sort algorithm on a subset of the input of data that you have for your problem. So, for example, if you want if you have a bunch of 2D points and you want to calculate the points that exist on the circumference of this spot, which is called the convex hull problem, it happens that you need to sort your points by their x values or y values, or both of them, okay, at a certain moment to solve this problem efficiently. As you saw in the previous video, one of the most efficient algorithms in searching requires that the list stays sorted all the time. And we consider the example of a phone book. So again, this is quite important, but and this happens to be one of the most studied problems in algorithm or algorithmic thinking. And you have an amazing number of fundamentally different algorithms that have been invented for sorting. It's becoming kind of the Formula One um, uh, for a particular subtype of Formula One for algorithm testing. And we will study a variety of sorting algorithms such as bubble sort, insertion sort, in this stack of slides, and later on merge sort when we learn about recursive algorithm. And of course, throughout your whole career as computer scientists or computer engineers, you will learn about plenty of other algorithms over time, sorting algorithms. Okay, so let's define it. The input of this problem is a sequence of and comparable elements. So we need to establish a certain order between every two elements. If I pick up a certain element AI and a certain element AJ, I should be able to tell whether AI is strictly greater than AJ, strictly less than AJ, or simply equal to it. Okay, so the elements should be comparable, so that they can be numbers, files, and comparing them by a file name or date of creation or size and so on and so forth, or by ID, or it could be a list of names and so on and so forth. The output is a certain permutation or kind of a reordering of those elements. They would become A prime 1, A prime 2, and so on and so forth, which is a certain permutation of the input sequence, such that A prime 1 is equal to one of those AIs, but simply it's less than or equal to A prime 2, which is also equal to one of those values, a different value, and so on and so forth, which is less than A prime n, which is equal to the last value that is different than all the previous value, or simply was not considered earlier, um, uh, and for example, in increasing order. Sorry, in this form when increasing order is sought. So the order can have varying definitions, not only to do with integers. Again, it could be any alphabetical order. I can create an order over shapes for 2D points. I can pick up the X order or the Y order. So it really depends on um, um, what actually serves me best. Okay, so it really depends on what I want to do with them. Um, and why do we study different sorting algorithms? Because there are a variety of situations that we may encounter when special sorting techniques are more suitable. More suitable means more efficient in terms of consumed memory space or consumed execution time. It means in terms of time or space complexity. So it depends whether the values that exist in the array are randomly ordered or maybe already pre-ordered and only one of them is not is out of order, so I need to put it back in its order. Is it the case that all the values, also called keys, are distinct? So, or do we have plenty of repetitions? So, are repetitions allowed? So, do I have something like 21, 3, 5, 7, and so on and so forth, 1 at the end, but never um, the same value twice? Okay. Um, how large is the set of keys to be ordered? So also depends if you have very large arrays or list of items. Certain algorithms becomes more efficient in this case, um, but they lose the battle if the array is small, relatively small, smaller than a certain threshold or size. And do we need a guarantee on the performance? And in this case, is it a performance or an average over all those cases, or in particular cases, or in the worst case scenario, and so on and so forth? So we'll see how this relates to different cases. Various sorting algorithms are better suited to some of these situations, so this is why we study different flavors of those algorithms. So let's start with one of the simplest algorithms, which is bubble sort. It makes multiple passes through a list, and every pair of elements that are found to be out of order are interchanged. So it's very easy to implement. And let's see the code first, and then we will see it in action, and we will understand in that moment why it's called bubble sort. So if we want to sort those elements, simply we make two nested loops. A first loop to iterate over the indices from 1 to n minus 1, actually, and another loop to iterate from 1 to n minus I. And if aj is strictly greater than aj plus 1, it means they are out of order if I want to sort them in increasing order. Then we interchange aj and aj plus 1. Okay, let's reinvent this algorithm on our own, actually. Well, actually, I have to exit those slides, and I'll go with you to OneNote. So if we want to reinvent this algorithm, let's think about it. So the idea is to make an iteration or like one pass over the values. So let's imagine we want to loop in this way. So for I equal 1 to n, okay, for all the values in the array, if ai is strictly greater than ai plus 1, then well, we have to swap AI and AI plus 1. So I think you already know about the technique to do it. So usually we would use a certain temporary value, because the core idea is to write kind of like AI equal to AI plus 1, and then AI plus 1 equal to AI, kind of, okay? But the problem is, if we execute this line, suppose that AI is equal to, here is equal to 5, and AI plus 1 happens to be equal to 3, okay? So actually, if we swap them, if I execute this line, well, we will copy 3 to AI, and then both values becomes equal to 3. If I copy back AI, the new AI that becomes 3 to AI plus 1, well, this is useless. What I want is to have a 3 up there instead of 5 actually up there instead of 3. So this is why we take, before screwing up the value of AI, before changing AI, we take a copy of it. Okay, so we use a certain, let's do it again correctly. So we use a certain temporary value. So first we copy the value of 5 to this temporary value. Okay, then we copy AI to, and now 10 becomes equal to 5. Then we copy 3 to AI. Okay, and then instead of copying AI to AI plus 1, we will actually copy temp to AI plus 1. Okay, and then we can replace this 3 by 5. Okay, then afterwards we don't care about the value of temp if we overwrite it in the future, because it's just really a temporary value to swap these two values. And if you know about functions, you could create a certain function called swap that takes in two indices, I and j in general, and just do this, actually temp equal to AI or AJ as you like, and then in the other one you put, or in the one that you just copied into temp, you put the other one, and then in that one you copy temp back, okay? And just call, instead of these 3 lines, call swap of I plus 1 in this case, and AI and I plus 1 will swap automatically. Okay, good. Sorry for those braces. I'm using Java or C++ notation, but you can use whatever you want. Just simple indentation if you're writing in Python. Good. So let's see what this would have done on a certain array of, okay. Suppose you have 1, 4, 3, and 2. Okay. After this pass, we will find that 1 and 4, they are in order, so we do nothing to them. But when we check 4 and 3, we see that they are out of order. So in this case, we will just swap them. So we'll put 4 here and 3 there, okay? And then we will compare 4 and 2, and we will actually swap them, because 4 is strictly greater than 2, and then we put 4 here and 4 at the end. Good. So after this pass, the highest value popped up to the end of the array. And by the way, as if this bubble has the, so every single value that we have has a certain quantity of helium associated with it, and the one with the highest quantity will pop up the highest, okay, to the highest position. So, and by the way, this is why we have this idea of bubbles, and hence the name bubble sort. But still, we have a higher weight here, okay, for this balloon that is equal to 3, and that is bigger than 2, but it wasn't put in place at the first, with the first pass, okay? And this is why we need to repeat this actually kind of n times, okay, to guarantee that we do this pass again and again and again. If you note, well, okay, so let's just write another loop. So for j equal 1 to n, repeat this once again. Okay, so on the next step, we compare 1 and 3, so they are in order. We compare 3 and 2, they are not in order, so we swap them. we put 2 here and 3 there, and then we compare 3 and 4, we find that they are in order, and then we do nothing afterwards. So this is the second pass, okay? Now we need to make another pass, okay? Just because to guarantee in the worst case scenario where 1 is on the right hand side and 4 is on the left hand side, then we will be doing this swapping again and again and again, okay? It happens that after the second pass, all the values are sorted, but this does not guarantee the worst case scenario. So this is why we need to check all the values. Well, actually, it's not totally true, because once you sort all those values, okay, so you notice that at the first pass, 4 is already put at the right place. On the second pass, the next highest value has been put at the right place. On the third one, in the worst cases, you will have the third value, and so on and so forth. So I think after sorting all these values, you don't need to make yet another pass. So this is why a fine tuning of this algorithm would be to consider j ranging from 1 to n minus 1. And if you check also the inner iteration, every time we do a new iteration, we know that in the previous one, the j different values, okay? So after j, when j becomes equal to 2, we know that for j equal to 1, the problem has been solved. So the highest value is already in place. So we don't need to do one addition comparison at the end. So I think we can range the values from 1 to n minus j, okay? So we can, sufficient to go from 1 here to 3 and not to the end to 4, okay? So, and this is why we have this, this algorithm here, okay? So just interchange j and I. So we build it step by step together. The first time we used up to n, okay, and we wrote this algorithm, we fine-tuned the swapping process, but afterwards we discovered that we need to do it multiple times. But how many times? Only n minus 1 time is required. So this is why we fine-tuned this limit. And also at every iteration j, the j first, the j last elements that we have in the array, they will be already in the right place. So we need only to go from 1 to n minus j, and all the values will be sorted. Okay, good. So now let's see it in action once again. So after the first pass, in the first pass, we go from 1 to n minus 1. So we check all the values. The original array is this one, 3, 2, 4, 1, 5. So we will see that 3 and 2 are swapped, 3 and 4 are swapped, or not swapped because they are in order. 4 and 1 will be swapped, and then 4, 5, no swapping because 5 is bigger than 4. At this moment, we would have made sure that the highest element is already in place. On the second pass, we will only go from 1 to n minus 2. Okay, so from here to this position here. Okay. Good. So we find that 2 and 3 they are in place, so we do nothing. We swap 3 and 1, and 3 and 4 they are at the right place. At this moment, we would have guaranteed that 4 is also at the right place. Okay, and now we do a smaller chunk. So every time we decrease by I, and at the end we have to check anyway that 1 and 2 they are in place. We do nothing, and then we skip. So maybe one optimization that comes to mind is the following. If at a certain moment, for example here, or actually at this moment here, so if for any reason you don't do any swapping between the values, okay, so you do a whole scan up to n minus I, because all the values from n minus I to n, they have been already sorted in place. So if you do a whole pass and you see that there's no need to swap any two different values, well, I think that you can say confidently that the array has been already sorted, okay? And an optimization for this code could be to break this for loop if you don't do any swapping, okay? So think about it in terms of break for the for loop, or and a certain counter, let's say, to check the number of swapping that you do, and you reinitialize it to 0 every time you start this for loop, okay? If the whole loop has been done and 0 exchange has been, or swapping has been done between the values, well, then you can here break the outer for loop. Good. So you have another example here that shows you more details. What about the other sorting algorithm? It's called insertion sort, and it's like sorting a hand of playing cards. So we start with an empty left hand, and the cards are facing down on the table. So we remove one card at a time from the table and insert it into the correct position, okay, in the left hand. And then actually, to do so, we compare it with each of the cards that are already in the hand from the right hand side to the left, okay? So imagine that you have already those cards in hand, okay? And you want to take from the table one additional card. So you have like, say, 3 here. So all the cards to the left are already sorted. You have 5 here, and you have the card 7, but you picked up a 6 here, okay? So if you want to put it at the right place, well, you actually start by testing from right to left. If it is if the number that you picked up is bigger than 7, well, you just insert it here. If it was 8, let's say. Otherwise, you make a place for the 6, okay? By, let's say, by copying 7 here, and just you replace it by 6. So you stop as soon as you find that the value, if you compare it with 5 and you find that it is bigger than 5, then you stop, and you would have made a space for the 6. Except that actually with the version that you will see, we are sorting the cards in place. So it means after sorting these 3 values, imagine you had them scrambled in a certain way. So 5, 7, 3, and then 6. Okay. Imagine that we arranged to sort 3, 5, 7 a certain way. By the way, it's the same way that I'm going to show you now, and you reach this card 6 that already exists in place. So what you do is you take a copy of 6 here in a certain temporary variable, and as long as you go back and you find that the values are bigger than the current value, the temp, well, actually, you remove the value and you copy the value that is behind it, okay? So you start from I equal to, let's say, the current position j minus 1 downward to 1, and each time, as long as it's bigger, you copy the values from the right to the left, okay? And then when you pinpoint towards 5, you see that it's less than 6, then you stop. You adjust the index to go backward to this place. You remove 6 and you put, 7, and you put 6 instead of it, in place of it, because you already took a copy of it in a certain temporary variable, okay? So it's an in-place sorting. You can go back to this original form and think about it. So when you start with 5, there's nothing to do. Next, you look at 7, you compare it back, and you see that 5 is less than 7, so you do nothing. But when you reach 3, you take a copy of 3, okay, and a temporary variable. And when you go backward, you just we don't remove 7 from here, but actually we remove 3 from this cell because it's less than 7, and we put 7 there. And then when we compare 3 and 5, we see that 3 is less than 5, so we copy 5 in this place. So even if we have the value 5 duplicated at a certain moment, it's not a big deal. And then at the end, when we reach the end of the array, we just copy that temporary variable in place. And this is how we could jump from this state to that state. Okay. Okay, the cards held in the left hand are sorted all the time. So these cards were originally the top cards of the pile on the table, and then we repeat until all the cards are picked up and they are put in the right place. So as I told you, it's quite similar, except that we are doing this sorting in place. Okay, so the code goes as follows. You can try to think about it on paper, and then check your answers. So the code, one of the versions is to start from 2 to n, okay, because the first value can stay in play, or actually will change its place. It has nothing previous to it to be compared with. So we take a copy for A2 and above, so for AJ. From j minus 1 and backward, as long as I is greater than 0, we decrement I. But at every moment, we check if AI is bigger than temp or not. If it is the case, then we copy it instead of it. Okay, so we put AI in AI plus 1. Okay, so we do the copy in those positions. Okay, in this way. We put actually AI in AI plus 1. But no worries, because even if we do this for the first time when AI is equal to j minus 1, so AI plus 1 would be equal to j, it's not a big deal because we already took a copy of AJ in temp, okay? And then when we finish, the position where we stopped, okay, it could be also outside of the array. So no big deal. So we just readjust it, and at AI plus 1, we copy the value of AJ, which is temp. Okay, we cannot put AJ anymore because it could be overridden by this instruction here. Okay, so we take the copy from temp and we put it in AI plus 1. Okay, good. So let's see it in action. So we have the algorithm here on the right hand side. In the first step, j is equal to 2. We have 2 and 5. We go backward as long as I is, so we start with I equal to j minus 1, it means I equal to 1. As long as I is strictly greater than 0, it's the case at this moment. And AI is strictly greater than temp. Well, it's the case because temp here is equal to 2. Okay, we would have copied AJ, which is A2, which is 2. So we actually, it is the case actually, 5, which is A1, is strictly greater than temp, which is 2. Okay. In this case, we have to copy AI plus 1 to AI. Sorry, AI to AI plus 1. So this is what we are doing. So we are copying A5 to, so A1, which is equal to 5 to this position. So we end up having 2 5s, but no big deal because temp is holding the value 2. We decrease I by 1. So now I is equal to 0. So I, it's outside of the boundary. But again, it's not a big deal because if I is not strictly greater than 0 anymore, okay? So we go outside of this loop, and then at AI plus 1, which is A1, we put the temp, which is 2. So we end up having 2 here and 5 there. Good. Can we stop? No, because we are inside the scope of a for loop. So j would be increased by 1 and becomes equal to 3. So let's see what would happen. In this case, temp is equal to AJ. It means A3, which is equal to 4. Well, in a few seconds, maybe A3 would completely change. So in this case, we will start comparing. We will go backward and we will compare A3, or actually temp with A2. Okay. It happens that A2, which is equal to 5, is greater than temp, which is equal to 4. So we simply copy 5 to this position. When we compare temp with A2, we find that 4 is not strictly less than 2. So we stop and we go outside of the loop. I is equal to 1, but we put at ai plus 1, which is 2, we put the value of 10. So we write 4 here. And this is why we end up with 2, 4, 5 at this stage. I think you got the idea, so we keep doing this. For example, 6 is put in a place because we stop checking from the first time. 1 is the smallest one, so we do all the copying from one cell to the other until we have 6 here, 5 here, 4 here, 2 here, and the place for 1. So we remove the 2 and we put 1 inside it. Instead of it. And then for 3, we have to get it backward until this position. Good. So we have just finished 2 of the most famous sorting algorithms, bubble sort and insertion sort. I hope that you find them clear, useful, and you master them. We will see actually later on how to reason about the complexity of those algorithms in terms of execution time and memory space. So stay tuned. Later on, we will check how to prove. So the next steps, we'll see how to prove by induction the correctness of the algorithms. And then we will see more about the growth of functions and how this can be a useful tool to reason about the, as I told you, the complexity of algorithms, typically the time complexity of algorithms, which relates to kind of the number of instructions that are executed by a certain algorithm. Okay, so this is the next step. Then those will follow afterwards. Stay tuned and see you soon.